Alright, so now we're going to start talking about, we talked about nuclear decay in that we've discussed the structure of alpha particles and beta particles and gamma radiation. And now we're going to use that then to talk about specifically the decay of certain isotopes and how we write nuclear equations and balance those. Okay, so those particle symbols we looked at in the last video, we're going to use in this. Okay, so let's just start with carbon-14 because that's pretty important. All right, so the way that you symbolize an isotope, there's different forms of carbon. All of them are going to have 6 protons, but they have different numbers of neutrons. And the different forms of carbon with different numbers of neutrons are called isotopes of each other. So it's all isotopes of carbon. You've got carbon-12, carbon-13, carbon-14. And carbon-14 is the one that's unstable. Okay? It will emit a beta particle. So it goes through radiation or goes through decay and then emits and therefore forms radiation called beta radiation. Okay? And what we saw previously in the previous video was that beta particles, we said, are going to have an atomic mass of 0 because essentially they're an electron. An electron's mass is so small we ignore it and we call it 0. I mean, we could write it in a fraction form, but it'd be like a really small fraction. It'd be 0.00, you know, really small. You know, like 3 zeros in a number, and that's just, we don't need it. We kind of ignore it for practical purposes, okay? But to make the math work out, because the pulling a beta particle or emitting a beta particle, it comes out of a neutron, it creates a proton. And for the math to work out, we'll show the atomic number as a -1. Okay? So what we need to do is to have all the atomic mass on the left side equal all the atomic mass on the right side. That's how you balance an equation, a nuclear equation. Okay? And the same is true for the atomic numbers. We have the atomic numbers on the left equal the atomic numbers on the right. Alright? So let's say we got a 14 here, and this number plus some other numbers got to equal 14. What's that going to be? Yeah, it's almost a trick question, isn't it? 14. Alright? And so we got a 6 here and a -1, so we need a particle over here that has what number? 7. And you look on your periodic table and find the element that has an atomic number of 7, nitrogen, and we've got a balanced nuclear equation. See? That's not so bad, is it? No. Just addition and subtraction. Alright? Let's see. How about, since what we were working with yesterday was a chunk of uranium ore, and that uranium ore had different isotopes of uranium in it. Okay? The most common isotope of uranium is 238. And what's the atomic number, and therefore what number do we put down here in the lower left? Look on your periodic table and tell me the atomic number for uranium. 92. Okay? And so, what kind of particles did we get out of that uranium-238 yesterday? Okay? So let's write an alpha particle where there's numbers here. It's going to go through alpha decay, so show me an alpha particle. (92). Okay? So, alright? Got that? So we're going to have some other particle over here to make the mass numbers equal on both sides and the atomic numbers equal on both sides. Yes, it is. The mass is protons plus neutrons. Okay? Atomic mass is protons plus neutrons. You already got it? So this number is going to be 234. And this number is going to be 90. 90 and 2 is 92. 4 and 234 is 238. And what element has 90 protons? Thorium. All right? Okay. Thorium goes through beta decay. Thorium-234 goes through beta decay. Can you write that equation? No, you got to do it as a separate equation because you're going to take thorium out and start over again. Does that make sense? Hmm? Yes, thorium-234. Beta decay. Is that what you got? Okay. That's protactinium. Well, protactinium goes through beta decay. We're back at thorium again.
Wait, I thought 92 was uranium.
Oh, I'm sorry. Is that right? What am I doing here? Oh, okay. Got it. Yeah, you go back to uranium. Got it. Got it. Go back somewhere. Okay. And then what kind of decay does uranium go through? Alpha again. And you go back to thorium. Then you go back to thorium, okay? Huh? Yeah. So this is, you'll find this in your test references. Okay? And it shows you the whole decay series. Eventually you get to lead. Huh?
Oh, I got it.
Make sense? Every one of these these angled arrows shows alpha decay. Every one of these to the right arrows shows beta decay. And so you keep going through the series until eventually you get to a stable element, and that happens to be lead. Make sense? Okay? Alright. Let's see, what kind of homework do we want to do for this? Just so you can practice something. No? You got to practice some, don't you? Yeah.
What dictates when it goes through alpha decay or beta decay?
Well, that's really, really complex, and you typically don't even try to cover that in high school at all. But there are people that are way smarter than me that figure out the math for how that happens. So you predict it according to the math. And in a more practical sense, it has to do with the structure and stability, because when you get to these larger elements, you get this, they become less and less stable. Okay? Which we're going to get to in a minute. We're going to discuss something called the band of stability. Yeah, at high school, we're going to tell you what kind of decay it goes through. You won't have to predict it yourself. Okay? So let's assume that you're working with plutonium-244. Yeah. It's a stinky element. Okay? And that'll be the first homework problem. So you can practice this on your own. Okay? What now? Same time. Just figure out the math. It's not that hard. Really isn't. Honestly.
So you're just going to end up with one equation?
Yep. There's one equation. So you have both the alpha and the gamma written on the right-hand side of the arrow, and figure out what the third particle is going to be. Got that? What?
I was trying to figure out how to say it was the stinky element.
Okay. Well, I figured after Devin said what he said, it was kind of obvious, but I guess. Okay, so that's your homework. Now, we'll move on to something else here. Okay?
After all homework, it's just that problem.
No, we'll probably assign something else here. Well, we're almost out of time, aren't we?
Mm-hmm.
We're going to set you up for understanding what's called the band of stability here. We'll finish it tomorrow. Okay? Talk about the band of stability. At least get you started on this. Okay? So if we take the periodic table, and remember all elements have different isotopes. Differing only in, what are the isotopes differing in? The mass, which is because they differ in the neutrons, okay? So all elements have different numbers of neutrons that are stable, different numbers of isotopes that are stable, and different numbers of isotopes that are not stable. Every element has this. Okay, how many of you are Spider-Man fans? Okay, oh good. One Spider-Man fan. Two? Oh yeah, we got 2, 3. Alright. So I hear 4. 5, 4. Okay. So, what was it that Dr. Octopus wanted to build his machine? Oh man, come on. Huh? Nobody remembers? Okay. He wanted tritium. Now, tritium is a very unstable isotope of hydrogen. Okay, that is so rare that there are probably only, I don't know, half a dozen atoms of tritium on the planet Earth. Okay, they're pretty common in the core of the sun, but not here. Okay, anyway, that's what he needed to make his fusion reactor one. Right? And that's what you use in the core of the sun for fusion. We'll get to fusion also. Try to get to that tomorrow. Okay, all right. So there are stable isotopes and unstable isotopes. But at a certain point, atoms get so big, you no longer have any stable isotopes for certain types, certain elements. Now, we used to say that beyond bismuth, there are no stable isotopes. So, polonium is unstable, astatine is unstable, radon is all the isotopes of these are unstable. Well, about 10 years ago, and I didn't know this until just recently because apparently I missed the article on it, or the articles on it, plural. Somebody figured out that bismuth doesn't have any stable isotopes. But here's what's cool about it. I think this is cool. Maybe you think I'm just kind of, a geek. That's okay. All right, I'm a chemistry geek. That's all right. All right? The half-life of bismuth is longer than the theoretical age of the universe. The half-life of the most stable isotope of bismuth is longer than the theoretical age of the universe. Huh?
We wouldn't be able to tell if it was decaying.
Yeah, pretty much. I mean, it does decay. We can test it. We know it's decaying. But half-life is the period of time, if you have one sample of bismuth, that half-life is the period of time in which half of those isotopes change into something else through some kind of nuclear decay process. Okay? So now our stop point is lead for the last stable isotope. Got that? So I have to kind of get it headed straight. If you hear me say 83, it's because I'm so used to it. I've been teaching for years bismuth was stable. And now I know it's not. So I have to be careful. So check me, okay? If you hear me say 83, oh, wait a minute, Mr. Tedder, it's really 82, remember? Okay? I mean, when you're doing it for years, it's kind of hard to change that in your head. But it's cool. It's changed. All right? All right, so beyond 82, there are no stable isotopes. But it turns out we can kind of predict in general when isotopes are stable or unstable. And here's how it works. Up to element 20, and this is kind of a general rule, all right? It's not specific, okay? You can't do the math and always predict it, but it's kind of a general rule. And we'll do the graph for this tomorrow. Up to element 20, stable isotopes generally, roughly, have an equal number of protons and electrons. I'm sorry, protons and neutrons. Okay? By the time to lead, by the time you get to lead, when I use the time in a sort of a colloquial sense, we're really just counting up the protons here, okay? But if you move up the periodic table, count 1, 2, 3, 4, 5, 6, 7, 8, and you get to 92, that's lead. Okay, by the time you get there, the stable isotopes have 1.5 times more neutrons than protons. Okay? Between 20 and 92, huh? Lead, 82. I'm sorry, lead is 82. I apologize. Lead is 82, not 92. 92 is plutonium. We're just using plutonium. Huh? Oh, did I say plutonium? Yeah, you're right. We did use that too. Okay. Between 20 and 82, there is a slowly increasing of neutrons compared to protons in stable isotopes. And so in general, you can kind of get an idea where the stable isotopes are located in terms of how many protons and neutrons by remembering this pattern. And we'll graph it tomorrow. But here's what you're looking at. Alright, so 82 is down here somewhere, 82. So between, so let's say this is 20 here. Okay, so we got 82 over here. This is the number of protons on this side, and the number of neutrons going up this way. Okay? So up to this point where 20 and 20 intersect, we've got an equal number of protons and neutrons. So you got a straight line, roughly. There are some isotopes that are stable on both sides of that line. Okay? By the time we get to 82, we want 1.5 times the number of protons in neutrons. Well, how many is that? What's 1.5 times 82? 82 plus 41. Huh? 123. So the number of neutrons is 123, and so they're going to intersect way up here somewhere. Actually, this is this line needs to be taller. But anyway, so you can't see it now because it won't look like a slope, but there's going to be a slow slope. This will slowly slope up to that point. Does that make sense? Okay, so this is 1.5 times the number of neutrons in the number compared to the number of protons to keep the nucleus stable. Make sense? So we'll graph this tomorrow. Also tomorrow, we're going to talk about fission and fusion. Okay? Anybody know what fission is? Splitting the atom. So make sure you write this down before you pack up. What is fusion? Okay. Putting nuclei. Who used that term a while ago? Stancil. Yeah. Nuclei. Okay. Putting nuclei together to make a larger atom. Or make a larger nucleus, technically. Anybody in here a music geek? No music geeks? Okay, you know what fusion jazz? No? Okay, there's different kinds of jazz. You put them together into one piece, you know, where you can't define it as one or the other, it's kind of both. It's called fusion jazz. Okay, what happens why do you set a broken bone? What's the purpose? So the two parts of the bone fuse together. Okay, so it's kind of the same word here.